Okay, so the back rows haven't really made much of progress forward. Trust me, move forward. Sadly, since this doesn't work, even the online lecture capture is not going to actually hear it. It will just be slides and me lip sync. Okay, let's get started. And if you can't hear me, I'm really sorry, but this is about the max I can go on volume without getting squeaky. Okay, so let's start with a recap of your exam, which was last Wednesday. Have we already blanked it out of our minds? Before we get there, today we're going to do gravitation. Since the beginning of this semester, you guys have been saying gravity this, gravity that. Let's actually analyze what gravity is and why some of us are so fussy on saying acceleration due to gravity versus the theory of gravity. Today we'll cover the theory of gravity. And I did ask you one question on the exam on the theory of gravity. So I'm going to reopen this as a clicker question. And you guys get to tell me what you wrote. Most of you got this right. And the right did come in inverted quotes. Don't change your answers. It's not for credit. What's on the exam is on the exam. It's all done. Then we'll go over why you said it and what the problem is. Okay, our logic in this question, well, the logic I'm presuming you guys did during the exam is that's the base of the building, that's the top of the building, it's some height h, right? The work done by gravity against gravity and going from this position to this position is mgh, right? And the logic was that since h is the same, it doesn't matter what path you take. The work done against gravity will be the same. It depends only on where you started and where you stopped. Correct? Okay, let's see if you guys got that far. So click the appropriate response. Yes, it's you both do the same work against gravity, essentially, because gravity is a conservative force. But here's the thing. H is the same. Nowhere in this question does it say anything about mass being the same. I didn't actually mean to do it that way. That was, as my friend calls it, a boo-boo. We assume, right, with an intrinsic assumption that your friend and you have the same mass. Because the work done is mgh. So it's equal when you have the same mass. And I don't know about you guys, most of my friends have more mass. Okay, so, yes, I did just call all of them fat. I'm not being recorded, so I can say that. Right. So, this question had an issue, right? The issue being, we assumed that everyone had the same mass, right? Because of that, I'm giving everyone credit on this question for the exam, regardless of what you're asking. But most of you got it right? With the assumption that they have the same mass, doesn't matter the path phase, right? Only changes in height. Everyone good so far? Okay, now today we'll spend time analyzing this second assumption. This guy, right? We assumed with the g, right, the acceleration due to gravity is the same for both you and your friend. And in fact, we assumed it's the same for every single object falling near the surface of the earth. Right? We did that in like week 1. Right? Okay, the idea today is to try and explain why. Okay. So, Newton's law of gravitation. I'm pretty sure everybody here has heard the story of an apple falling into Newton's head. And that the Eureka moment came up with this theory of gravity. I'm not too sure if there's any truth to that story whatsoever. realize that stuff falls down. Correct? Right? That wasn't the law of gravity. What Newton's genius was that he realized that the same force that's responsible for apples falling near the surface of the earth is the force that's responsible for the moon orbiting the earth. The same force is responsible for the earth orbiting the sun. Right? So Newton's genius is realizing, first off, that all mass, right, regardless of what it is and where it is, attracts other mass. Okay? This force of attraction is related to how massive these objects are, and it's related to how far they are from each other. Right? His other realization was that this force of gravitational attraction drops off at the distance between the objects. Everyone with me? Right? So the law of gravitation basically came to say all mass attract each other. Right? And secondly, this force of attraction drops off at the distance between the objects. Everyone with me? So when we say all objects that have mass attract each other, obviously the Earth is a bunch of little objects of mass, right? And it's held together by gravitational attraction. Saturn, for instance, masses around some planets, right? They're held in orbit around that planet by gravity. Right? Entire galaxies, okay, like planets, stars, spinning around each other. Okay? All of this is happening because of gravitational forces between these large planets. Everyone with me? And the same force is causing apples to fall. Right. So, any two objects will exert a gravitational force on each other. The magnitude of that force is given by capital E, which I'll come to in a minute, times M1, M2. M1 and M2 are the two masses. Right? So, the larger the masses, the larger the force. And the force is directly related to the product of these masses. Okay? R is the distance between. Right? And like fundamental forces, like other fundamental force you will see later, like next semester, it's a 1 over r square dependence. We'll come to that in a bit. This capital G is called the universal gravitational constant. Its value is really 6.67 times 10 to the minus 11. Think of the number of zeros after the decimal. Okay. It's called the universal gravitational constant because its value is constant anywhere in our universe. Okay? It doesn't matter if you're on Earth, on Mars, on a different solar system. The value of capital G stays the same. Right? It's a universal constant. Right? This is the first universal constant we're coming across this. Right? And we call it the universal gravitational constant. We do not call it gravity. Gravity is the entire chapter, it's theory. Okay? Little g is the acceleration due to gravity. Capital G is the universal gravitational constant. Right? It is not an acceleration, it is just a constant. Right. On on everyday objects, right? So essentially, you all have mass, right? You're not calling back, it's mass. Right? So what this theory is telling you is that all of you attract each other with a force directly proportional to the product of your masses and inversely proportional to how far away you are from each other. Does that make sense? Okay, you don't feel it, right? Right? I mean, while walking around, you don't feel random people towards people around you. That would be weird. Right? The reason being that value, capital G, is so small, right? That the value of everyday forces between objects of regular mass is negligible. Right? So like a backpack on a girl, like it's a heavy backpack, 10 kilograms, it's not like finger weight. The force between the backpack and the girl is 10 to the minus 7 newtons. Right? She's not going to feel it. Right? But if one of those objects is the earth, right, then she will feel the force of the earth on her. The mass of the earth is 6 times 10 to the 24 kilograms. 700 newtons on the girl, how much force should the girl exert back on the earth? The earth exerts a force of 700 newtons on the girl. How much force should the girl be exerting back on the earth? The same, right? From Newton's third law. Correct? Every force has an equal and opposite reaction. You get the same force if you plug it into Gm1 and 4 r squared. There is same distance apart, they have the same mass. Right? It's just one force acts on the earth, the other force acts on the earth. Correct? And if you remember Newton's second law, if the force is equal, of course, different masses have different accelerations. Right? So, which one accelerates more, the girl or the earth? The girl, right? Presumably she doesn't weigh as much as the earth. So, the earth has a large mass, therefore it has a small acceleration, which is negligible. And the girl, on the other hand, has a small mass. So, for the same force, she experiences a large acceleration, right? Which we call the force she is experiencing per weight. Everyone good so far? Right? And the direction of this force is attractive, right? So it goes between the center of mass of the girl and the center of mass of the earth, right? So if you were to draw it, like that's the earth, that's the girl, right? Regardless of where she stands, this force of attraction is towards the center of mass of the earth. Correct? So it really doesn't matter if she's in Australia, right? The force of attraction is still that way. This makes sense? Right? Everything, like gravity acts like around the surface of the earth. Gravity acts towards the center of the earth. Right? That's what we mean when we say these forces are attracted. Right? Their centers of mass go towards each other. Everyone with me? Right? Okay. Now, that distance dependence. So, if that were to plot, right, the force of gravity between two objects as a function of the distance between them, right, it drops off as 1 over r squared. Right, which means if I double the distance, what am I doing to the magnitude of the mass? If I double the distance between two objects, what do I do to the magnitude of the force between them? I decrease it by what factor? 4, right? 2 squared. Similarly, if I triple the distance, it would go down by a factor of 9. Right? So that's an inverse square law dependence. It means it depends on the square of the distance between them. Right? And this isn't something you experience. Right? What we're saying is that as objects are further apart, the force of gravity between them is less. Correct? So you on the ground here versus you on the top of Fox Hall. In theory, the force of gravity on you at the top of Fox Hall is less, correct? Right? If I took a scale to the top of Fox Hall and I stood on it, my weight would be less. No. Right? No. Theoretically, yes, but not in any measurable fashion. Right? And we'll come to that. Why have we assumed so far that the acceleration due to gravity is constant? Right? That assumption must have limits. Everyone with me? Okay. We're going to do some math today, but let's start with easy concept questions. Well, easy is a relative term. Oops. I had the old poll open. Right, let's try this one. The Earth and the Moon are, of course, two large objects. They are expected to attract each other gravitationally. I'm asking you which one holds harder. Good. They pull on each other. The force is increasing, right? The one that will accelerate more is the smaller mass, which of course is the moon. Right, so click the appropriate response. Right. Okay, let's try this one. We are now doubling the distance between the Earth and the Moon, and I'm asking you what happens to the force between the Earth and the Moon. Ooh, you're taking your time on this. You double the distance, right? Should the force increase or decrease? It should decrease, right? It's an inverse square force, right? It's not an inverse force, it's an inverse square. So it goes off with the square of it. What is 2 squared? 4, right? It's got to drop by a factor of 4. Does that make sense? Because the object moves further apart, right? The factor is 2 squared. It drops by a factor of 2 squared, which is called a quarter, right? 1/4. Let's see if you guys got that. Yes, you did. Good. Don't worry, we're not done with this. Two objects now, M1 and M2. M2 is smaller than M1. But in this case, I'm asking for the gravitational acceleration of both these objects. I am not asking for the force. What must be true of the force? The force must be the same, right? You can turn it off. So which one should accelerate more? This guy or the big one? It's the same example, but like what you can think about. Still works. Right? Same force, given different mass. The little case will accelerate more than the large. Correct? Right. Good. Click the appropriate response. And then pull out a pen and a pad. Okay. Now you can do this in your head. I would suggest writing it out. Okay? Just because a lot of times we'll change more than one thing. So you want to see a cumulative effect. Right? Over here, all we're doing is doubling the mass, right? And we're doubling one of the masses. Correct? So if I double one of the masses, let's see, my initial force between them is G M1 M2 over R squared, right? Let's call this F1. I double the mass of one of the objects, the force becomes 2m1 m2 over r squared, right? So F2 is 2 times F1. Everyone with me? Right? So double the mass, double the force. If I double just one mass. If I double both masses, what happens to the force? What happens to the force if I double both masses? Goes up by a factor of 4, right? I'm going to keep the doc cam on for a second because we'll need it. Right, so click something. I am just doubling one mass in this question, not both. Okay. Yep. Now, This is the question that I was talking about. I'm changing multiple things. Right? You can do this in your head. If I were to do this in my head, and I double both the masses, right? So if I double both the masses, by what factor have I increased the force? 4, right? I also have the distance in between these masses. If I have the distance in between the masses, am I going to increase the force or decrease the force? I'm going to increase the force, right? They come closer together. Adding the distance, you are coming closer together. Increase the force, right? You half the distance, which means you change the distance by a factor of 2, right? Correct? So what should happen to the force? Should it increase by a factor of 2 or 2 squared? How does gravity depend on distance? Inverse square, right? So it should increase by a factor of 2 squared. So this question is saying that our mass change gets us an increase of 4. Our distance change gets us an increase of 4. What is the total increase? 16, right? It's 4 times 4. Correct? And you can do that mathematically. So if I were to do it out, this is my original force, right? I have doubled both the masses. So capital G doesn't change. Both the masses double. Right? And I half the distance in between them. Right? So R goes as R over 2. Right? Do the math out. This is 4 up top. This is 4 M1 M2 over R squared over 4, which is 16. Right? So 16 times my original force. I didn't open the question, so it's fine. Right. What I want you guys to do now is find these, consider an object of mass m in free fall in a surface of the Earth. Right? And find its acceleration. So, I'm going to set up this question, and you will be able to do this question for any planet other than the Earth as well, right? The same method. So, our method is, this is the surface of whatever planet I'm considering, right? So, this is the Earth. So, this is the radius of the Earth, right? And we are given that the radius of the Earth is 6.38 times 10 to the 6 meters, right? We're asked to consider a mass of some unknown mass m, right, in free fall near the Earth's surface. So at that point, what is the only force that acts on it? If it's in free fall, what is the only force acting on an object in free fall? Gravity, right? Everyone agree? Okay, so I'm going to just put Fg on it. Right? The force of gravity. Everyone good so far? So from Newton's second law, we can say that Fg, right, the force of gravity, since that's the only force acting on it, it must equal ma. Right? Net force equals mass times acceleration, right? I'm looking for that acceleration. Everyone with me so far? Okay. Fg is given by capital G m1 m2 over r squared. This must equal ma. So let's call this mass m1 and the Earth m2. Right? Those are the two masses. Right? Okay. So this becomes G, little m, mass of the Earth, over r squared is little m times a. So I can divide out that little mass, right? That unknown mass goes away. It's divided out. Everyone with me so far? Okay. What do I use for r? What is r supposed to be? In Newton's law of gravitation, what is R supposed to be? Distance between these two objects, right? Correct? Is the distance between these two objects this guy or this guy? How? Is it this or this? The distance to the center of mass, right? Correct? It's not the distance from the surface of the Earth, right? It's the distance from the center of the Earth, right? The R in Newton's law of gravitation is the distance between centers of mass, right? The center of mass of the Earth is at the center of the Earth, correct? So this distance, right, that goes into this law is actually based on this figure, RE, the radius of the Earth, plus h, right? However high above the surface of the Earth this thing is. Everyone with me? So this expression becomes G me over RE plus h the whole squared is equal to a. This makes sense to everyone. I'm going to pause here for a second. Look at that expression. Right? We're saying that the acceleration of this object falling near the surface of the Earth, right, is capital G, some constant, times the mass of the Earth, divided by the square of the distance between the center of the mass. Right? Okay. Now look at that term, RE plus H, and look at the value of RE. Right? The value of RE is 6.38 times 10 to the 6 meters. Right? To put that in perspective, right, it's 6.38 times 10 to the 3 kilometers. Right? So that's 6.38 thousand kilometers. Everyone with me? It's a really, really large number. Right? Ordinary distances near the surface of the Earth are very, very small compared to that number. Right? The top of Fox Hall doesn't need to register as a limit, right? That's how many significance you have to get to actually factor that into that calculation. This makes sense? So I can neglect those distances. Right? So if I neglect H as compared to RE, so we're saying that since H is much less than RE, RE plus H is approximately just RE. Right? We're adding a really, really small number to a really, really big number. Right? So we're just going to ignore the really, really small number compared to that big number. Okay? Now, you end up with an expression then that looks like A equals G me over RE squared. I have given you the values of me and the value of RE. Capital G is 6.6 times 10 to the minus 11. Do it. Can someone tell me without doing that what that number would be? What? 9.8 meters per second squared. Right? That fun number you got in chapter 2. This is why it's true. Right? The acceleration due to gravity near the surface of the Earth is 9.8 meters per second squared. You measured it in lab. Right? This is just showing you how you get that and what it depends on. Right? This is why when you go to a different planet, if you talk about the acceleration due to gravity on the moon, on Jupiter, right? It's different. The theory of gravity that applies on the moon and Jupiter is the same. Right? The acceleration due to gravity is different, the mass of Jupiter is different, the radius of Jupiter. Correct? Okay. So the value of acceleration due to gravity near the surface of the Earth is found this way. You can do the same thing to find the values of acceleration due to gravity on other objects, right? Like, we'll come to Jupiter in the end, I believe. Okay. We've all seen videos of people in space, right? Correct? They seem weightless. Yes, they're all flying around, right? On their ships. Correct? Are they actually weightless? No. Right? Because the term weightless implies no weight, which implies no gravity. Right? They're in orbit around the Earth. So yes, they're far away, but the Earth is still pulling it. Correct? Right? So why do they appear weightless? Right? The answer, of course, is it's the same thing as, plummeting in an elevator. The weight is mg. Objects in space will still have weight. So if I was to do the astronauts versus the ships, ma, right? Both are equal to mg. Correct? The force of gravity on them. Right? It's capital G m1 m2 over r squared. For the astronaut, it's capital G, mass of the Earth, mass of the astronaut divided by the square of the distance. For the ship, it's mass of the Earth, mass of the ship divided by the square of the distance. Right? And if you notice, if you find their accelerations, the masses of the ship and the astronaut cancel out. Right? And you're left with the same acceleration for both the ship and the people in it. Right? And this is what is weightlessness. Everything around you is experiencing the same acceleration. Right? So there is no reason for you to be on the floor because the floor is falling at the same rate as you are. Does that make sense? It is literally like being in an elevator with the cord breaking and you and your grocery bags are floating down at the same rate. Correct? But imagine yourself in an elevator holding groceries. Cord breaks. You can let go of the bag. Right? On your way down, the bag is going to stay right where it was with you. And you can marvel at that while contemplating the end. This making sense? Right? The reason for this is everything on the ship and the astronaut is all falling at the same rate. Right? So there is no pushback from the ground. Right? So you don't feel like you're standing on anything. Because in order to feel like you're standing on something, you need a normal force from the ground. Right? Which will only exist if that's not accelerating much. Correct? Okay. By the way, there are actually several medical issues related to space travel, or actually being in space for a long period of time. One of the things is muscle loss. Right? Main reason for muscle loss is the simple act of walking, standing, running around, which you do in ordinary circumstances. Takes work. Right? It exercises your muscles because you're fighting against gravity. If you're in a weightless environment, right, there's no reason for that exercise. You don't naturally get that exercise. Does this make sense? The other slightly more subtle problem, I believe, is severe blood loss. Right? And we cover this again when you do fluids. But when you're standing, right, blood goes down. Right? Gravity. There's more blood down there than up here. And by the way, that's the same reason you take blood pressure measurements at the same height. Right? So that you're not getting pressure variations. Okay? Anyways, so there's more blood down there than up here under normal circumstances. Right? When you're on the Earth. Because gravity is acting on your blood, taking it down. Right? When you're in space, in apparent weightlessness, there's no reason for that pooling of blood up or down. So it distributes itself uniformly. Right? That distribution, making it uniform, means now that up here there's more blood than there was. Right? So these vessels swell up. Your brain thinks, oops, too much blood. Right? So it cuts blood on. Does this make sense? Right? So there are medical issues with being in an apparently weightless environment. So while it may be fun, people do need to get trained. Right? And while they're up there, they need to exercise a lot. Good reason for me to not go up. Right. So all objects accelerating at the same rate appear weightless. Okay. This is not true weightlessness. Right. If I were to ask you what is the acceleration due to gravity on the surface of Jupiter, do it. This is very similar to setting up the acceleration due to gravity on the center of the Earth. Actually, it's pretty much the same problem, just the two. The reason I want you guys to do it is you're dealing with big numbers. Okay? One of the problems with gravity is you're dealing with really big or really small numbers. Right? So get some practice with your calculator. Right, so you should set it up so that the m divides out, right? We don't care which mass is in free fall. So the acceleration due to gravity near the surface of Jupiter should be capital G times the mass of Jupiter divided by the square of the radius. So if and when you get this question on an exam, remember to start from there, right? Okay, you plug in all those really, really big numbers, and this is the important part. Remember, you get credit for showing these steps. Right? Show this step. Show us which numbers we're plugging in, simply because there is a fairly good probability that there will be some typo in typing those numbers into a calculator. Okay? Because they're very big. Right? And I don't want you losing credit just because of that, so show me this step. Right, and then you calculate and you find that the acceleration due to gravity on the surface of Jupiter is significantly higher, as expected. Right, it is significantly more massive than the Earth. Now, if at the end of the day there is one question I want you to answer, right, and go away, it's this: why isn't the moon in my vacuum? Right? The Earth is pulling on the moon, right? The direction of that force, if I were to draw it, is that's the Earth, that's the moon. That is the force of gravitational attraction, right, between the Earth and the moon. It's directed straight towards the center of the Earth. Correct? Right? So why isn't the moon at the center of the Earth? Like, why isn't it here? What is the moon doing? Let's spell that out. What's it doing? What? Orbiting, right? So it has an orbital speed. Correct? Right? What is the direction of that orbital speed? Tangent. Very good. So this guy is actually doing this. Right? It has a V, and it has a force actually perpendicular to V. Right? What happens when forces act perpendicular to velocity? What does the object do? Wednesday's exam. What does the object do if forces act perpendicular to velocity? Goes in a circle. Correct? So the moon goes in a circle because it has tangential velocity. Right? If gravity suddenly failed, what would the moon do? It would fly off, right? It's exactly the same as a ball on a string. The string breaks, right? The ball goes flying. Correct? If the moon slows down, it is flying. This makes sense? Right? So because the moon has a tangential velocity, the force of gravity is actually providing a centripetal force. Right? It's the force responsible for making this thing move in a circle. Everyone with me so far? Okay. This takes us to the heart. One thing to conceptually understand this, but now let's actually discuss it mathematically. Right? So click something. Yes, it has a high tangential velocity. So, good. Right. The moon is a satellite, right? Okay. It's an actual satellite, but you can have artificial satellite. A specific kind of artificial satellite is real in space, is called a geosynchronous satellite. Right? When we say it's geosynchronous, what that means is its location above a fixed point on the Earth is fixed. Right? So as the Earth rotates, the satellite stays above the same position on the Earth. Correct? Okay, so for a geosynchronous satellite, how long does it take to do one complete revolution? Remember, geosynchronous meaning that for a fixed point on the Earth, right, the satellite has to stay right above. How long does it take for a geosynchronous satellite to complete one revolution? 1 day. Right? In order to stay at the same point above the Earth, you have to rotate at the same rate as the Earth. Correct? The Earth's rotation period is 1 day. So this satellite's rotation period is 1 day. Everyone with me so far? Okay. Now comes the math and the drawing. So the drawing actually looks a lot like this, right? This is my satellite, which has some mass, which I will say is the mass of the satellite. This is the Earth. It's the mass of the Earth, the radius of the Earth. And this is what I will call the orbital radius of the satellite. Right? Look at R0 and R1. These are two different radii. Right? Radii of the Earth is a constant, some fixed number. Right? R0 is the orbital radius of this satellite. Right? It is RE plus some h. Right? Some height above the surface of the Earth. Everyone with me? Okay. For a satellite, is it a valid assumption for me to say that h is less than R0? No. Right? Satellites can be really, really far away. Right? They're pretty much in space. Correct? They're not near the surface of the Earth. Right? It's not like moving around at the height of Oxford. No. Way, way, way high. Everyone with me? So we cannot make that assumption. Right? So in this case, the orbital radius is what I'm asked for, and that's what I must find. It's not the radius of the Earth. This makes sense? Okay. Let's start by writing Newton's second law. So sum of forces on this satellite must equal mass times the acceleration of the satellite, right? So this is mass of the satellite and acceleration of the satellite. Everyone with me so far? Right. What is the acceleration of the satellite? It's moving with a speed v in a circle of radius r. What is its acceleration? Moving in a circle, so not zero. Moving in a circle with speed v, the circle has a radius r. What is the acceleration? V squared over r, right? Centripetal acceleration. Okay, so this becomes sum of forces is ms v squared over r0, right? The radius of the orbit that the satellite is moving in. Is everyone with me so far? We have to keep track of our radii, we have to keep track of which mass we're talking about. Right? Right now we're talking about the satellite. Right? The satellite is moving in an orbital radius of r0 and it has a mass ms, right, with a speed v. Everyone good so far? Okay. The left-hand side of this equation is the force of gravitational attraction between that satellite and the Earth. Right? So this now becomes capital G, mass of the Earth, mass of the satellite, divided by the square of the distance between them, which is again r0. Right? Because the distance between the Earth and the satellite is the orbital radius of the satellite. Everyone with me so far? Okay. So equate these two, and you get ms v squared over r0 is equal to that much. Now, do a little bit of algebra. the mass of the satellite goes away, right? So this equation, one of these r0s cancels out, and we find that the speed of the satellite, v squared, is gme over r0. Does this make sense?
I'm a little confused on the radii. So is the radii the complete distance from the center of the Earth to the satellite?
Yes. So her question was about the radii. She asked if the radius is the distance from the center of the Earth to the satellite. Right? And that is correct. Right? It's always from the center of the object to the center. Okay? Not from surface. Right? So it's that full R0. Right? Which includes the RE. Right? That R0 is greater than RE. So it's included in that the radius of the Earth is included in that value. Right? Okay. Before we move forward, look at this equation. This is saying that the speed of a satellite, right, in orbit around the Earth depends on the mass of the Earth, which we cannot change, right, and the radius of the satellite's orbit. What does it not depend on? It doesn't depend at all on the mass of the satellite. Does that make sense? Right? So what we're saying is that a heavy satellite, a light satellite, it doesn't matter. Right? What determines its speed in orbit is how far away it is from the Earth. Yes? Okay. We're not done. There's one more step. We need to find the orbital radius, right? I haven't found the orbital radius. I know the mass of the Earth. I do not know R0. I do not know V. Right? I do know, however, that this satellite takes 24 hours to complete one revolution. Right? So the speed of the satellite is 2 pi r0, which is the circumference of one complete revolution, divided by t, which is 24 hours. Right? So I can substitute v is 2 pi r0 over t into this expression, and it becomes 4 pi squared r0 squared over t squared is equal to g me over r0. I am left with one unknown. Right? In this equation, while it looks complicated, there's only one thing you do not know. Right? It has to be radius of the orbital. Correct? Okay. As practice, just because you guys will probably have a little bit of difficulty dealing with these numbers, I'm going to give you the number, right? Please try doing it at home and try getting the same number. That will get you practice on your calculators of dealing with these really massive numbers. Okay? The number you should get is like 4.2 times 10 to the 7 meters. Okay. One quick important announcement. Your pre-lecture assignment is due on Wednesday. We start a new chapter on Wednesday, so the next pre-lecture assignment is going to become available in about a minute. It's due by 8 a.m. on Wednesday. Sorry?